and we want to provide
This meeting
data
is
for
being
those
recorded.
instructions. Ideally, what we would like is memory that is infinitely large and infinitely fast, right? So that would take care of all our needs. Now, that's unrealistic. So maybe pretty large and pretty fast. At the very least, we would like it to be as fast as the CPU and large enough to hold whatever we want to do with it, right? So if I, let's see if I can pull it up. If I go to a computer, more likely um, for individuals to start looking at, then you would be talking about something like the IBM PC with a 4 gigahertz processor, and it would have 16 to 256 kilobytes of memory. And if that wasn't sufficient, then it would have removable storage, right? And if we take a look at the picture, not very much screen space, no mouse, just a keyboard. And there is actually no hard drive on this device. There's just a pair of these floppy drives right here and a nice big solid on off switch. None of that power down mode or sleep mode or hibernate or any of that. And none of that color nonsense either, just black and white. So, since we're not going to get large and fast, we will lean on the principle of locality. Even though we may have many programs loaded in memory, we're not going to be running all those programs. We'll be running fewer programs because we don't have as many processors. And the processor itself, we're not running all 10,000 lines of your program. We're running one line in a non pipeline architecture, a handful of instructions in a pipeline architecture, and realistically, a bit more in a superscalar architecture, right? We also know that if the instructions are in a loop, if they're the induction variables, the loop variables, then those will be variables we access over and over again. Instructions in a loop, we will repeat. And so we will see those instructions over and over again. We will see those data items over and over again, right? So that's temporal locality. And I'll definitely ask in chapter 5. For spatial locality in terms of questions. In this case, though, instead of looking at it from a time point of view, we're looking at it from space, right? And so if I get an instruction and it's not branching, then we know that we're looking at program counter plus 4 to get to the and so forth. If I'm accessing an array item, most likely I'm going to access array item plus 1 and so forth as I move through the space of my memory. So what we end up doing is building a hierarchy. Since we can't right now physically buy or build memory that's both large and fast, we can buy fast memory and we can buy large memory, right? And if we go back to that IBM PC from 81, so that's close to 45 years ago, that didn't even have a cache. So we basically had the registers for the CPU, and they were very small and only a handful. And then we had memory. So the disparity between those two in performance and space was quite large, right? We had lots of space and memory, but we had the speed in the registers. And so the hierarchy was not very deep. And then if we add another level of the hierarchy, we would have had those floppy disks or eventually a hard drive. Nowadays, instead of a hard drive, we have an SSD, but still a permanent storage solution that if we lose power on our device, we don't lose our data. And so our programs will get loaded off the disk, secondary storage, the network, the hard drive, the SSD. It will be placed in main memory, RAM, and then we'll initialize the program counter and tell it, here is where you need to go to get it, right? And so we'll ask for it, but that's still a disconnect in performance between the CPU typically made at generally was better fabs and at a higher fidelity, right, and a higher speed versus memory, which is typically sort of an older fab, larger size. And so we need to have a cache. We need something intermediate between the fast CPU and the large memory. So things that we're accessing frequently with temporal spatial locality, loops, sequential instructions, those will be small enough in number because we don't have that many registers to fit in a small cache, which is a fraction of the size and can better match the speed of the CPU. So that's the entire idea between what we're going to be talking about here in chapter 5. But what we'll do is go under the hood and take a look at how this gets implemented and therefore what constraints that places on performance, and therefore what might we alter when we reach the end of the chapter of our program to help make our program run faster. So we've got our processor, our cache, and our memory. And nowadays the cache has multiple physical levels, but here we're just looking at a logical representation. We typically don't want to access just a single data item to fit in a register. We want to get, oops, I should not wave my hands around or turn off the bubbles. But we want to copy multiple words. So we call multiple words block. Line is a really old term, such as copying a line of data because of how they were physically arranged in sort of linear lines, and you would access, even if you had a large set of memory, you would access it a line or a row at a time, right? What you're hoping for is a hit in your cache. And the hit ratio is the hits per access. So you're hoping that number is really high. Ideally 100%, but that's not going to happen. But hopefully in the high 90s. If it's a miss, then the data is not present in the cache, and I need to get it from a lower level cache or ultimately RAM. So that's going to be slower than the CPU, slower than the higher level cache, and so that's the miss penalty, the time it takes, that how many cycles I'm going to have to wait in order for that data to be ready for me to access it. And of course, then the ratio for the misses is 1 minus the hit ratio because it's everywhere we didn't hit. And then once we have satisfied updating from the lower block, then we can proceed. And hopefully then maybe we're pulled in a block that we don't have a miss for a while as we work our way through the contents of that next block. So underneath the hood, there's a variety of ways to build the RAM, right? So one thing is leaning on Moore's law and getting finer and finer resolution for your components, right? How small your transistors are, because ultimately at this point time in this day and age, all of the RAM and the solid state drive are built out of transistors, right? But different organizations. And you kind of sort of what you want what you do is you add a bunch of transistors to help facilitate making it fast. On the other hand, down in the SSD, you might have less transistors per bit of data, but therefore then you can have a mass volume of transistors to have lots and lots of data, right? So when we talk about solid state drives or magnetic drives, secondary storage in both cases, we talk about nowadays gigabytes or even terabytes. Actually, we do talk about terabytes. I got mine confused with RAM. All right. So secondary storage, typically, if you're at the low end, you're talking about hundreds of gigabytes and going up into terabytes, right? So I have a laptop, it's a Mac. I wanted to save some money. Secondary storage is famously expensive for Macs. So I only have half a terabyte of storage in my main storage, secondary storage. Then RAM, dynamic RAM, static RAM. Static RAM is faster. You can get it in read only and read versions. So you can have a ROM on your machine, which might have things like the BIOS or memory that is always there when you power off the machine, especially useful for embedded devices. And we can see an order of magnitude difference in performance between the fastest RAM and the dynamic RAM or standard RAM that you're running inside of your memory system, but also a significant difference in price. And then again, a significant difference in price by many orders of magnitude, but going from nanoseconds to microseconds or milliseconds in access time. Right? So fast is the access time of the fastest RAM, the static RAM, and large is the capacity of a magnetic disk. And they still exist. So for RAM, we're really looking for volume, right? And we're not building it at the same resolution that we're doing with the CPU. So we can build it in cheaper fabs with a cheaper process and also large volumes. And we're really looking for a reliable build process because we're looking at billions, if not trillions, of identical elements in order to build RAM, right? If I'm talking about my laptop has 16 gigabytes, so 16 times 8 is you're looking at over 100 gigabytes. So, or 100, over 100 gigabits, right? And then later on in the chapter, we'll see that we need some error handling, error detection. So that expands on the size. But if I'm looking at 100 billion bits, I need lots of transistors to both hold that information and move that information in and out of the RAM, right? And I'm not going to read a bit at a time or even a byte at a time. I'm going to read a row, right? I'm going to read a row as part of banks, and you can see that regular structure. If you see the physical RAM, it's layered, it's in modules. And of course, in order to make RAM perform really well, it's always active and it must be refreshed. And of course, that's why it's volatile and goes away when we lose power. Additionally, we have to have a bus that connects the RAM to the CPU, and that bus has limitations on its performance too. And then I'm not really going to delve into all the physical parts of RAM, plus I haven't really kept up as much. It's been over a decade since I last pulled the computer apart to install RAM. Nowadays, I just buy it as what it comes with. Especially that's a limitation of the MacBooks. But we have our bits and our bytes and our rows, and then you can access rows in what's called a burst mode. So that speeds or reduces the latency as you dedicate everything to reading from the row or writing to the row. We talked about at the beginning of chapter 4 that we've got our clock with its cycle, and that we were using the change in the clock. So when it changes from high to low or low to high, and the option we were using in chapter 4 was on the rising edge. So each clock cycle, the rising edge, we update our system. And we keep that limitation because of the complexity of what's happening in the CPU and our stages. Accessing RAM or data is not that complex per se. You don't have as much circuits devoted to all that. So what we can do is do double data rate. So as our clock rises, we access. As our clock falls, we access. So that's DDR RAM. Transfer on the rising and falling clock edge. And then quad RAM, at first we maybe have, our 8 wires to get a bit. Well, let's double that again so that not only can we read in the same cycle. So we'll separate our inputs and outputs. Right? All of this takes more resources, rate. So that's one thing that you've also, if you read up on the technology of RAM, then you read that not only are they working on, higher performance, higher capacity, but now they're started looking at optimizing for power consumption, right? So they were finding that memory was starting to take up a large chunk of the power consumption on the machine. And so now we want to also manage that too and keep that from getting out of hand. Right? Because with quad data rate, essentially we're accessing 4 times as much stuff in the same amount of time, and that takes power. So this chart, and this is where RISC sort of came about too in the 80s, is that the RISC approach to computers said, well, wow, memory is expensive. So originally computers had powerful instructions that didn't take up a lot of space and storage and didn't take much effort to transfer because it was small and compact. And that was the x86 and many of the architectures pre-80s. And so then as memory prices dropped dramatically, you see that here, I could make smaller instructions that do less work, which then facilitates usage in a pipeline, but it then dramatically increases the storage requirements of my, but memory's cheaper and faster, so I can get away with that, right? So we can get a trade-off there. Try to be able to better do things, utilize our instructions in the CPU, but the trade-off is we need cheap, fast memory to make that work. And so I added the bottom line just to sort of show as capacity increased, prices decreased over the past 40 years or so. And realistically, the thing to get from all of this is we're trying to improve the bandwidth. How wide can we transfer information to and from the RAM, right? We'll do it in bursts. We'll do it simultaneously. We'll do it across a wider and wider bus in order to make all of this occur as fast as possible. And if we have multiple RAM chips, then not only can we move from a narrower channel to a wider channel to multiple channels accessing multiple RAM chips across our bus, which then connects to our cache and then connects to our processor. And then if you look at something like Apple's M1 chip, we'll push all of this into a single piece of silicon, onto a single chip. So then that puts it very close together and very, very fast, right? Because they've realized now the data needs of many of the modern applications is so high that we really want all this to be as fast as possible and as close together as possible in order to make this happen. So currently, any of your, I would call them sort of front-leaning devices, your phone, your laptop, your desktop computer, your game console, they're all going to use SSDs, right? There's flash storage, more expensive, but faster, and with the ability to be persistent, whereas RAM is not. That's sort of the flash storage that we might get on an embedded device or a BIOS, or be able to have as a portable SD card. And then we've got our SSD devices also. Again, there's a variety of different technologies in place. Just as we really didn't get into it in chapter 4, but the nature of how the transistors were built and what materials were used and how they're organized has definitely changed over the last 40 years. And so the same thing here. We have a version of Flash for embedded systems. We have a version of Flash for media, USB devices. One downside to the Flash type memory is it wears out. So you still have a market for longer term devices, but modern operating systems and their file management maps the data across to make sure that it's consumed all over and it just doesn't keep focusing on one spot. Also, this is typically over 10 years or a dozen years, right? So I, for example, had a computer that had an old SSD, and by the time I decided to get rid of the computer, the SSD was still working just fine, and that was about 11 years later, so over a decade. And I mean, if this is what you're using in your phone, how many people typically are still using a phone, the same one, after a decade? Especially younger audiences. But it does make you think that if you want to keep something around, maybe not just put it on a SD device, SD card, find something a bit more resilient and also back it up across another device, such as cloud storage or something else more permanent, like, for example, disk storage, right? These have been around for many decades. So, since the 70s or so. And so they're well known, they're very reliable. You can buy super ultra reliable versions of these with high speed. It's not as fast as SD, but it also has large volume. So I ask, does anybody have a hard drive in a computer in their house?
Yes.
So I do.
It's the backup computer.
It's the same thing for me. I have a Synology DiskStation, and I use that to back up my MacBooks. They all connect to it in my Macs and my iPad. And also, but, my my phone, my laptop, my desktop, my tablets, my game console, no hard drive, right? But there's still a place for it. And my hard drives weren't that cheap. They weren't super expensive, but I bought high reliability, something like what Alex mentions there, NAS with terabytes of storage for my photos, my financial records, and any other files that I want to keep around. And since I've been sadly disappointed with how streaming has worked itself out, I have backed up bunches of CDs and DVDs and stuff like that. So it still has a place, and I think it'll still have a place for many decades to come. Even if not eventually in your house, it'll still be out there in industry. So these kind of devices, you can see the physical arm. It's got magnetic reading capability, and it moves across. And the slowness of this is you have to wait till you have to move the arm to the track you want to read, and then you have to read the sector, which is in the block, right? When I taught an operating system course back in the day, one of the projects that I would give students would be to write some their own file manipulation programs to be able to go into the file system and read out from the file system what's stored in there. So they would have to pull in the sector ID and the directory access information. But seek, rotational latency, the actual transfer, the controller to connect it to the bus, all of these give us, we don't really need to delve into these numbers, but all of these give us access times that are in the milliseconds rather than microseconds. On the other hand, if this is like Alex has NAS, some sort of backup server, it's sitting on the network. So we're already dealing with network transference times, and then we're not per se running programs directly from these devices, but we may be accessing or transferring data, and we're willing to put up with that to get larger capacity. And I won't ask you to derive any of these kinds of stuff in any of the homeworks or the tests. And it's been a really long time since I've delved into the ins and outs of these, probably over 20 years since I last looked at for things like, for example, SCSI drive versus an ATA drive, an SAE drive, what kind of components, because back in the day, if I tried to build a computer, right? Nowadays, I'm pretty much happy with having something pre-built for me or just using what's the defaults available. They have the performance that I'm expecting. Okay, so before I delve into the cache, I did want to show you sort of a video.
Provides the structure for the assembly, and it has a row of male pins here, and the leads from the matrix will be welded to the pins.
So that one logic stick can be connected to another one.
That's right. Let's take a look at how the operators do this operation in detail. This operator is loading the little micrologic elements into the comp header. This socket, and
For 38 and
loaded with cores. We're then ready to do the wiring. In order to perform the wiring operation, we store about 20 feet of wire in this needle. See how that wire comes out of there? Now the operator will take a core holder and pass the needle through.
So this is an MIT. There's actually 30 minutes on this. The first 10 minutes is the operation of the Lunar and Apollo computers, their interface and stuff, and it's interesting stuff. The next 10 minutes is the CPU stuff. So I probably should have shown that back in the day. And then the last 10 minutes, which I'll show you, is what memory looked at in the 60s. So instead of transistors, they used wires to hold the information. So this is called core memory, right? And so I thought it'd be interesting to compare and contrast what we have today with what they have. So this will give you an idea of what they had back.
To the core, around to the other side, and then weave it back through a different position. Now let's watch how the girls do this operation in a little more detail. Now here we have a pair of girls who are wiring the address wiring of the core rope module. Now they pass the wire back and forth, stored in the needle, and put it through the cores in a particular wiring pattern. Now each time a wire goes through, they must very carefully wrap the wire around one of those little nylon pins. As you can see, what that does is pull the wire away from the center of the core to allow room to pass the needle through again.
I see. Now these address wires go to every single core?
That's right. Now when the wire is completely weaved into the rope, it must be terminated on a little solder. Now the girl strips the insulation from the wire and very carefully wraps it around the pin. Then they use a magnifying glass to inspect their work. Now the sense wiring information, or the wiring that contains the program of the fixed memory, is performed by using this machine. The machine indexes to a particular location of a core, and then the girl passes the needle through the aperture and provides the wire to go through the right core.
She doesn't have to think about which core it goes through next.
No, the machine does that for her. Now note, each time the wire passes through, that little aperture jogs down and pulls the wire around one of the nylon pins. When she passes the needle through, she will trip the switch with the needle, which causes a tape reader to advance. There's the tape reader, and that in turn causes the core rope plane to move its position. Now, after all the wiring is completed, these nylon pins that we use to temporarily hold the wire can now be removed. Next, we must press the wires very gently down into place so we'll be able to fold up the whole assembly. Now, this operator is folding the core planes into a sandwich-type construction and laying them into the header of the module. Now we're ready for electrical test. We must ensure that every wire and every component are properly located. The operator puts the module into this piece of special test equipment, and a program stored on paper tape is then used to exercise the module.
But this is certainly a complicated-looking maze of wiring in here.
That certainly is, John. That module contains 512 cores and over a half a mile of wire. And it performs the function of storing over 65,000 individual pieces of information.
Tell me, do you put that potting compound all over this, too?
Yes. Now, in the final form, here's the module potted, and it's all ready to be plugged into the memory tray assembly.
Tell me, how do you connect one module to the next one in these trays?
Well, that's done on the back side of the tray. Let me show you.
Oh, I see.
Now, here you see a fairly complex wiring pattern. We're able to interconnect from module to module by running wires from this pin to, say, that pin.
Right.
Now, this pattern is so complex that we've used a computer program to determine the exact layout of each wire. That is, we may run a wire from here to here by going down this way and over here and up there.
Why is that?
Well, that's to avoid a density problem where the wires could build up if we laid them all in the same channel.
Oh, I see. But I should think that would make it rather hard for somebody who was trying to wire from one pin to another to remember all
Well,
that.
that's true. In fact, the wiring is so complex that a human being just can't do it. So we use a machine to do all of this wiring. This is the automatic wire wrap machine. The operator has placed the tray in the machine and is starting the wiring operation. Now, this machine has two wire wrap tools that can be incremented to the proper location on the tray. When it's found the right pins, the wire is stretched out and formed in the right pattern. Then the insulation is stripped from the ends of the wires, and finally the two tools drop down and wrap two pins simultaneously. Now, in order
around corners and things?
Yes, you can. And in order to run the wire in a different direction, sometimes the tray is rotated. It can be positioned in 4 different locations. Now, the information to command those wire wrap tools is contained on these IBM cards. Each card has the information for a single wire.
How is the wire actually fastened to the pin? Is it soldered or welded?
No, this is what's known as a wire wrap connection. The soft copper wire is very tightly wrapped around the pin, and you might see that the pin is a square-cornered pin. And in this fashion, the wire digs into the sharp corners of the pin and provides a good electrical connection. Now we're entering the computer system test area, John. After the trays have been potted and the modules assembled to the trays, we bring the machine into this area and run through exhaustive temperature tests and vibration tests.
I see.
Then finally, we must perform a complete electrical checkout of the computer. Now, this piece of equipment is the computer test set. This provides a means to enter data into the machine and monitor all of the various outputs. Here we have a piece of equipment that provides the power and interconnects the computer to the 2 display and keyboards.
Now, what kind of tests would you perform on it?
Well, actually, we've written a very special fixed memory program that allows the machine to test itself. As an example, we can have the machine test that all the possible displays can be created. Let me show you. Now, as I enter that, we see that the displays go from all 9s to all 8s and so forth down the line.
Now, is this the last time that the computer is tested before it actually is flown?
No. The computer will be tested several times as part of the guidance and navigation system. In fact, the same type of equipment that we have here will be used for these various tests.
Thank you very much, Mr. Pounce. Today, we visited the instrumentation laboratory at MIT and the Raytheon Company in Waltham, Massachusetts. I'm John Fitch, MIT science reporter.
So in this case, if you're listening carefully, each of those modules, 65,000 bits, so that's only 8 kilobytes, right? And they only had about a dozen of these, and this would be the permanent storage. So this was both the hard drive, RAM, and cache. So this was everything. One memory location for the permanent programs on board the spacecraft, and then they had one of the earliest transistor-based computers, still individual transistors, so not an integrated circuit, to run the spacecraft itself. And it's interesting to hear about things like square pegs to hold the wires, and that they're not soldering those wires, they're simply wrapping them. And then they got women who worked in textile factories who came in and did the sort of, the weaving for this core memory system. Times have certainly changed from there. As I mentioned, the first 10 minutes is the operation of the computer, which you saw an example of the computer there. It had a noun, verb, and double-digit system. You would enter in a verb, you would click verb and the digit for the verb, and the noun and the digit for the noun to make things happen. Okay, so nowadays, we've got our RAM, our CPU, and in between them, the cache, right? And so what we want to do is, when we look at the cache, we want to ask ourselves, how do I find something in the cache? And then we also want to ask ourselves, if it's the location where I'm supposed to find something, is it actually there yet, right? especially in a program that's just started running or hasn't been running at all, then most likely it's not there yet. So is it data item 2 or 3 or 1 or 4? So what we'll look at initially this week is a direct map cache system. And so this simplifies the placement of items because there's only one choice, right? I don't have to look anywhere else. I don't have to search. And that adds extra complexity. Instead, I just do some math, right? I go, memory's large, and it's larger by several multiples of my cache. And I'm going to divide that memory into blocks. I'm going to divide my cache into blocks. And then I'm going to use the modulo operator. So here we see that modulo operator show up again from Fundamentals 1 and get the address by modulating across the blocks in the cache. The downside of this is less flexibility. It also means that, and this is a problem with any cache, the cache is smaller than memory. Therefore, I'm only going to be able to hold part of memory in the cache, and which parts of it I'm going to be able to hold. In this case, what it does say is that, for example, this blue location, 101, we're using the modulo on the low order address bits. This maps to across memory all the blocks that the low order bits match, 101, 101, 101. But that also means in this particular example, given this size of memory and this size of cache, there are 4 blocks which all share the same cache address. So I can only have one of those 4 blocks. But since they're spread out, ideally I might be able to say, well, program A is here, program B is here, program C is here. And I can therefore get away with doing this. So which of those blue blocks is the one that we actually want? Well, we still need to reference the other bits as part of the address, the high order bits. So that's called the tag. We don't need to have the lower order bits. We just simply use the modulo operator to give us the block that fits that. And then associated with that block, we will then have the tag, which has actual bits, which are used to hold the high order bits. And then the last piece of the puzzle is, okay, we're referencing this memory location, but is it actually occupied? So if it's valid or present, we'll have a 1, otherwise we'll have a 0. So we need another bit for that. So however big our block is, it's not really in this case, it's specified as 1 word for block. So we would be saying 32 bits. We've got 8 blocks. So 4 times 8 is 32 bytes worth of data overall in our cache. And then we've got our index, which will take us directly to the relevant block. Is the data actually present in that block? Yes, no, 1, 0. And then is the, what block is it from RAM? And so that's where the tag comes into play. So in this case, we're using this direct mapping, and this is on slide 20, the initial state. It's empty. There's nothing present. We're ready to go as our first program. So the first thing we ask for is, as an integer, the word address 22, in binary, 10, 1, 10. With 5 bits. What is that, like 32 different options? Obviously, it's going to be a miss, and we want cache block 110. So we come down to 110. We will then make a request to RAM, And once that request is fulfilled, we'll mark this as yes. We will take the higher order bits, fill in the tag, and then whatever's at this location, 10110, we will put that in here. That was definitely a miss. So that has the miss penalty going to RAM. So we keep doing this, right? So we'll do another request. It's a miss. But it doesn't conflict with the first one. And then we'll ask for those two things again, right? This is temporal locality. We're asking for the same thing at a later timestamp. And then we'll ask for three more items. The first two will be misses. The third will be another. And eventually we'll start filling up memory. And then this will get to another problem is once we're filled up our cache, what do we do next? Right? So that's also something to consider. But before we get there, the downside of a direct mapping is a lack of flexibility in placing things. So even though we have free blocks, if we ask for another block that has the same 3 low order bits as a block that's already loaded, we would have to replace it. So this one's at 10.0110, and that was currently occupied by 11.010. So I got to replace it. I need to use it. I'm not currently using the other one because I moved on and I didn't discard anything because that would be a performance thing too. So it's still a miss and I get the new information. You see, all right. And so this is where we'll stop for today. We request an address. We're not accessing at the bit level. So the last 2 bits in a 32-bit address, if I discard the last 2 bits, then I am asking for words. And so I'm looking for words or bytes. Let me think. Yeah, we're looking for bytes. So it's a byte offset if I'm ignoring the last 2. And so in this model, I'm going to make it bigger. So I'm going to use a 32-bit address space, which is 4 gigabytes. I'm going to have 10 bits for the index and 20 bits for the tag, right? And so then I still have my word data blocks, but now instead of having 8 of them, I've got 1,000 of them, right? So with 10 bits, 2 to the 10, so approximately 1,000, plus I got my valid bit, plus I have my tag. So the address, I'll pull out the tag, I'll get the index, that tells me here what I'm matching for, and then I'll check the valid bit, that's our AND gate, and then this is a comparator, and so this is a bit of logic that's on part of the cache, and I will then compare the tag here for the address I'm asking for to see if in this direct mapping version, is that the actual match? If that's a match and the valid is a match, my AND gate returns true, and that's a hit. If either one of them is false, then that's a miss. And if it's a hit, I will also transfer the data over to the CPU. So this is a good stopping point. We'll start expanding on our notion of what we might do to increase the performance, both by looking at different ways of mapping things and also looking at other characteristics of the RAM and cache. So I will see you on Wednesday.
judicious choice. Hundreds of hours, 98.56 hours from launch. And it also gives me a fine view of the low order part of the time in seconds and hundreds of seconds. That is useful occasionally.
I should think yes, around launch time. That'd be interesting.
Yes. The computer will continue to display that information until told otherwise. And it's told otherwise by another verb. In this case, the verb is terminate. 34. It's now forgotten that command.